Hey, let's take a look here at section 8.4, talking about matrix inverses. Okay, so first let's talk about something involving things we already know. So if we've got a real number valued equation here, so all the coefficients are real numbers, all the variables are assumed to be real. This is what we've been dealing with pretty much so far in our math career. We know what to do with this, right? If we had that, our goal to solve this is to get this piece alone, right? So what we have to do is first get rid of that 3 on this side. So we're going to add 3 to both sides, right? Adding 3 to both sides. And that would give us 4x plus 0 equal 8, right? Usually we don't write this, but just for illustrative purposes, why not? The reason that's 0 and why we want to emphasize that is that right here we're adding the inverse of -3, right? So we're adding whatever number it takes to give us the additive identity, which essentially makes it go away from that side of the equation, right? Because we can write this as, 4x equals 8, because that 0 is just pretty much not there. It's the identity. We know that if I add 0 to any number at all, I just get that same number back. So we just, 4x. And now on this one, we know what to do here. We want to apply the multiplicative inverse here. So if I multiply both sides by 1/4, well, that is a number times its multiplicative inverse. So we end up with its identity right there, right? So then 8/4, that's 2. So now, again, we've got the multiplicative identity, and we don't usually write it. We usually just write x equals 2 because, hey, 1 times anything, it's just that thing. Okay, so then we've solved it, right? One very critical difference here between what we're about to talk about is that we multiplied right here on the left, on the left-hand side, we multiplied on the left, and on the right-hand side, we multiplied on the right. Now, in the last section, we spent a little bit of time saying that matrix multiplication is not commutative. This is where that's a big deal, right? Because when we're looking at something like this, if I have that all of these things are these matrices, it would look like this, right? Now, we can do the same sort of thing that we did over on the right-hand side, but, if I call that A, then I'm going to have to multiply by the inverse of A on that side, and then maybe I'll put that in a different color. If I want to get the variable part alone, that is, if I want to make this be the identity in front of the variable, we're going to have to multiply by the inverse of A, right, whatever that is. And importantly, we need to multiply by the same thing. That's the inverse, right, of A. We have to multiply both on the same side, very importantly. So this writing inverse of A, that's super clunky, and we don't want to do that. We want to have nice notation for this, and we're going to use the same notation we used for functions with that -1 business. So we're going to call the inverse of A inverse, right? And it's going to have that notation where we've got, it looks like an exponent, but it's not, right? Okay, so I think I wrote, yeah, there we go. So we got a definition here. So an n by n matrix is said to be invertible if there exists a matrix so that when we multiply it by that matrix, if I multiply A by A inverse, then I necessarily need to get the identity back. So our goal at this point is to be able to find such an object. For addition and multiplication, it's easy, right? So for 3, I would just take the negative of that number to find its additive inverse. For 4, I would just take the reciprocal of that thing, 1/4 for its inverse. And we can do the same thing for every real number. Now, it's not going to be as easy as we want it to be to find matrix inverses. So let's do this one. Let me write this up here. So I've got 2, -3, 3, 4. Okay, so we're looking for an inverse of this guy. Let's say it's this. If I want the inverse of this, it has to be another matrix that I can multiply by it, and it's got entries, A, B, C, D, whatever they are, we don't know. But when I multiply those two inverses together, we need to get the identity back, and that's that 2 by 2 identity. So what we can do here is, well, I guess we can multiply these two matrices together, or matrices, right? We do that row by column business. So here we can put, maybe I'll just write that here. We got row 1 times column 1, row 2 times column 1, row 1 times column 2, row 2 times column 2. And we can say what that is. So we got row 1 times column 1. We're going to have A times 2 minus 3 times C. And then the row 2 column 1, we've got 3A plus 4C. Okay, and now we move over to the next position. So what have we got? Row 1 times column 2. So row 1, column 2. So we got 2B minus 3D. And then row 2 times column 2. We got 3B plus 4D. Okay, so that's going to be the left-hand side, right? And then that has to be equal to 1, 0, 0, 1, which is the identity, right? So what we see here is that if I have two matrices that are equal, they have to be, first of all, be the same size. And these are both 2 by 2, right? This is 2 by 2 and this is 2 by 2. And we also have to have all of the variables have to be, or excuse me, not the variables, all of the positions have to agree. So whatever's in this position has to be the same as this, right? Whatever's in this position here has to be this. So we can write that down, right? We have to have 2A minus 3C has to be 1, and we have to have 3A plus 4C has to be 0. And we've also got that 2B minus 3D has to be 0, and 3B plus 4D has to be 1, right? All of these positions have to agree with their corresponding position over here. All right, now we've got two new systems, and we can solve these. Well, let's start out by rewriting these as augmented matrices, because that's what we usually do, right? So we got 2, -3, 3, 4, 1, 0. And we've got 2, -3, 3, 4, 0, 1. Now, hopefully, when we wrote these down, we see something that is very, very, very convenient. So check it out. On the left-hand side, those are both the same, right? So conceiving in our minds what it is that we're going to do to solve this system, we're going to use that the reduced row echelon form, right? So in practice, we're going to be doing the same operations to solve both of these. So why don't we just do it all at once? So that's what we're going to be doing. We're going to do it all at once. Let me get down here. So notice that the row operations to solve the two systems. So let me rewrite what we had here just so we can see it again. Well, I'll just push pause. Okay, so now we've got the two systems from above. You know, why don't we just rewrite it? You know, we're going to be doing the same row operations to solve both of them. So why don't we combine those two? Combine these. So through 2, -3, 3, 4, and then on the right-hand side, why don't we just put these here? So that gives rise to what we just wrote right here, right? So what we're going to end up doing here, again, is the same for both of these matrices. So just do it at the same time. And what's going to happen is, once we have this in reduced row echelon form, which will be exactly this, right? The identity of size 2. We're going to have the inverse on the other side. So let's do that, and then we can verify it. Okay, so here's the system we want to solve, right? Or excuse me, we don't want to, we're reducing the left-hand side to the identity. So our goal is to end up with the identity here. So we want to essentially put whatever is in the right-hand side, that's the identity, and we want to make the left-hand side look like that with using row operations. So in my mind, what the easiest step here would be, if I want to make this a 2, or excuse me, I don't want to make that a 2. It already is a 2. We want to make it a 1. I'm going to go ahead and flip-flop these rows first and then subtract row 2 from row 1. And that's going to be an easy 1 to get, right? So why don't we do that? So I'm going to switch row 1 and row 2. And we're going to start here. And we're flipping row 1 and row 2. So we got 3, 4, 0, 1, 2, negative 3, 1, 0. Okay, that was easy enough. And now we can take row 1 minus row 2 and put that in place of row 1. Okay, so doing that is going to be pretty quick, right? Row 1 is, we got 3 minus 2, that's 1. 4 minus negative 3 is 7. 0 minus 1, 1 minus 0. Easy enough. And now we do the usual thing. To get rid of this 2 right here, we're going to just take row 2 and subtract off 2 times row 1. Put that in place of row 2. Arrow. Okay, row 1's not changing, so let's just copy that down. And then row 2 is going to change. We're going to have row 2, so we got 2, minus 2 times row 1, that gives us 0. We got negative 3 minus 2 times row 1, which is 7. So negative 3 minus 2 times 7 is 14, so that's negative 17. 1 is in this position, so row 2 minus 2 times row 1, that's going to give us 3, right? 1 minus negative 2 would be 3. And then row 2 minus 2 times row 1, we're going to have negative 2 in that position. Okay, let me make that look more like a 17. There we go. All right, and now what? Now we want to have a 1 in that position. And our hand is sort of forced here. We're just going to have to take negative 1/17 times row 2 and put it in place of row 2. We can write that right here. So row 1's not changing. We got 1, 7, negative 1, 1. And then row 2, we've got 0. Negative 1/17 times 17, negative is 1. And then we got negative 3/17 and positive 2/17. So the fractions have reared their ugly heads, but we'll get rid of them. Well, we'll be done with them here in the next step. Okay, so what is the next step? We want to get rid of that number. So I want to do row 1 minus 7 times row 2 and put that in place of row 1. Okay, so we can do that. Change in row 1. So we got 1 minus 7 times 0, 1. 7 minus 7 times 1 is 0. That's good. Negative 1, probably want to write some scratch work here with the fractions. So we got negative 1 minus 7 times row 2. That would be negative 1 plus 21 over 17. So that's negative 17 over 17 plus 21 over 17. So that's 4/17. Right? 21 minus 17 would be 4. Great. All right, now we move to that next position. We have what? Row 1 is 1 minus 7 times row 2, 2/17. And okay, so that's going to be 7/17. That's 1. Minus 14 over 17, so that's 3 over 17. Okay, great. All right, and then row 2 didn't change. We got 0, 1, negative 3, 17, 2/17. Okay, so what this tells us is that this is the inverse. A inverse must be the thing that's on the right-hand side now, because we transformed that into our solution of what we wanted. So there we go. There's our inverse. So let's go verify that actually worked. And let's go put that back into the context of what it was that we were talking about in the first place. So we had an equation here, right? We had an equation here, and we wanted to solve this thing. Well, check it out. If we've got our equation here, I want to take, and if we take our well, let's not get ahead of ourselves. Let's not get ahead of ourselves. We want to verify that this is the inverse first. So we want to take what we just found, which was 4/17, 3/17, negative 3/17, and 2/17, and we want to verify that we have the inverse of this, 2, negative 3, 3, 4. So if this is the inverse, this has to be the identity when we multiply them together. It must be the identity. Well, let's see what it actually is. So again, when we multiply these together, we're going to have, I'll write it up here, row 1 times column 1, row 2 times column 1, row 1, column 2, row 2, column 2. So that's what we're doing here. So our first position, top left, we've got our row 1, column 1. So we've got 4/17 times 2 plus 3/17 times 3. Our next position, we've got row 2, column 1. So row 2, we got negative 3/17 times 2 plus 2/17 times 3. Okay, great. Now we move on to the next column and the first row. We've got 4/17 times negative 3 plus 3/17 times 4. And then our next position, well, we're at the same column, just the second row, negative 3/17 times negative 3 plus 2/17 times 4. Okay, so now we just compute these things. Well, 4 times 2 over 17, that's 8/17 plus 9/17. Well, that's 7/17. Okay, that's good. Down in the bottom left, we've got negative 6/17 plus 6/17. So, hey, that's 0. Top right, we have negative 12. Negative 12/17 plus 12/17. Well, that's 0. And in the bottom position, we have negative times negative is positive, so 9 plus 8 over 17. Well, that's 1. So hey, it worked. Happy days. What a wonderful method to find inverses. So yeah, we're going to do this a couple more times, but what we ended up doing, again, just to recap here, to find our inverse, we knew that I had to have another matrix. We just called it ABCD. And if we multiplied those together, we had to get this identity back. So that gave us 2 additional systems here to solve. And they ended up being the same thing, right? So we're going to do the same row operations to solve both of these, which is what we did. We just ended up putting the matrix that you want the inverse of on one side, and the matrix that is the identity of that size on the other. And then we just did row operations until we had the inverse on the left, and then the thing on the right is necessarily our inverse. So hey, that was awesome. Now, if we wanted to go and solve that original equation that was written, we had AX equal B, and what that ended up being, what was that? Our matrix was 2, negative 3, 3, 4, and we had XY. And then we had, what was that matrix B? It was 16. That's 7. So what we can do is we can say, hey, if I apply the inverse on both sides there, that will be the identity of size 2. And that's essentially just 1, right? If we're thinking about it in terms of real valued equations. But then on the right-hand side, we're going to have to actually do this matrix multiplication. So that A inverse, again, was 4/17, 3/17, negative 3/17, and 2/17. And all we have to do is just multiply. So in the end, we've got our variable matrix has to be, well, the product here, which is going to be the first row times the first column, column 1, and the second row times the second column. Let me just rewrite those. And there is no second column, so that's it. So we can do this, right? Row 1 times column 1. So we got 4/17 times 16 plus 3/17 times 7. And then we have negative 3/17 times 16 plus 2/17 times 7. And we can go ahead and compute that really quickly here. That's not exactly the difficulty here. Let me just pause this and do that real quick. Okay, so when we multiply all these out, hey, we get 5, -2. So there's our solution to this matrix valued equation. Okay, cool. So now let's do it again. So this is going to be a good example here of the fact that it doesn't work all the time. So maybe notice back up in that definition of what we said for inverses, kind of glossed over what it said. Not every matrix has an inverse. So not every matrix. Is invertible. So that's kind of a big deal because this will correspond to systems that have no solutions, right? So what we're going to find here is that we're going to do the same steps. We're going to try to do the same thing. So we're going to try to put our matrix given here, and we want to put our identity on the other side, and then we want to solve this. Okay, so if we can make this be the identity, then that means this matrix has an inverse. But if we can't make this be the identity, that means the matrix, doesn't have an inverse. So let's do this real quick. Okay, just kind of trying to think about the easiest way to get a 1 in that position. What could we do here? Well, why don't we, because if I take 2 times 3, that's 1 away from 5. So I can use 2 times row 1 and subtract off row 2 and put that in place of row 1. Okay, and that's going to give me a 1 in that top position, right? So 2 times row 1 is 6, minus 5 is 1. 2 times row 2 here is 7, minus 12 is 2. 2 times row 1 is 2, minus 0. 2 times 0 minus 1 is minus 1. And then this row didn't change. Alrighty. And now we can do what? We want to get rid of this 5. So we want to take 5 times row 1 and subtract that from row 2. So row 2 minus 5 times row 1. Put that in place of row 2. Okay, row 1 didn't change. 1, 2, 2, -1. All right. And then row 2 is changing. We got row 2 is 5 in this position. Minus 5 times 1 is 0. 12 minus 2 times 5 is 2. 0 minus 2 times 5 would be -10. Oops. And then 1 minus 5 times -1 would be 6. All right, no fractions yet, so that's not so crazy at the moment. Okay, cool. So now we want a 1 in that position. So we can just do 1/2 row 2, put that in place of row 2. That's an easy step. So we got 1, 2, 2, -1. 0 times 1/2 is 0. 2 times 1/2 is 1. We got -5, and we got 3. Okay, and now what? We want to get rid of that guy. So we're going to take row 1 minus 2 times row 2, put that in place of row 1. All right, and we can do that. We've got 1 minus 2 times 0 is 1. 2 minus 2 times 1 is 0. 2 minus, so just maybe scratch work, 2 minus 2 times -5, that's 2 plus 10, so that's 12. Okay, and then we've got row 1 in the top right, we've got -1 minus 2 times 3, so that would be -7. Okay, and then the second row didn't change. Okay, cool. So that means that if I call that matrix A, then that tells me that A inverse must be 12, -7, -5, 3. Okay, cool. And of course, the process gets a little more, longer, I guess, if we have a 3 by 3 matrix or even a 4 by 4 or 5 by 5. It gets considerably longer and longer to do the process, but the process remains the same, right? We just want to get whatever size identity we have here, right? Identity of size 2, and then our inverse matrix is on the right-hand side, right? So that tells us that. Okay, cool. So we found the inverse, and it exists, and we can verify that. Maybe we can leave that to you to multiply it on both sides and see that we do get the identity, because you will. But I think this is the example that I was trying to lead into at first, because not all matrices are invertible. If we cannot make it so there's the identity on the left, that means that the matrix is not invertible. So let's take a look at this one. So yeah, we just want to set ourselves up just like we were before. So what we've got our matrix C, and then I'm going to put the identity of size 2 here. So we've got 6, 15, 14, 35, and then the identity of size 2. All right. And now we want to make this into 1, 0, 0, 1, and then our inverse is going to be on that side, right? Okay, so this is our goal, right? So let's try to make it happen. Well, these are both even. What if we do multiples of I don't know. If there's not an immediately clear thing to do that makes it easy to get a 1 in this position, sometimes it is just the best just divide everything by 6. So if I take row 1 here and divide everything by 6 and put that in place of row 1, that's gonna do my immediate goal here, right? 1/6 of 6 is 1. 1/6 of 15 is 15 over 6. But we can write that as 5 halves, right? Because both of those have a factor of 3. Then we got 1/6, and we got 0/6. Okay, and then this row didn't change. Okay, so now we want to get a 0 in that position there. So what we're going to do here is do row 2 minus 14 rather, row 1, and put that in place of row 2. Okay, so row 1 is not going to change. 1, 5 halves, 1/6, 0. And then row 2 minus 14, row 1, in that position is a 0. Let's do some scratch work here. So row 2 is 35 minus 14 times 5 halves is what we want to put right there, right? So we can do this. 14 divided by 2 is 7. 7 times 5 is 35. Well, that's 0, okay. And then we have the rest of it. So we've got row 2 in this position, we got 0 minus 14 times row 1. And if we reduce that, that's 7/3. Okay. And then 0, row 2 here is 1 minus 14 row 1 would still be a 1. Okay. So at this point, we can see that, well, that thing here is 0, 0. And this is going to indicate to us that we're not going to be able to get a 1 in that position. So that says that this is not invertible. C is not invertible. So more or less, if we try to do this process and we are unable to make the left side look like the inverse, the identity, then we say that C is not invertible, and we're just done, and that's it. So that's pretty convenient for us. When it breaks down like that, we're just finished. We say it's not invertible. Okay, so we've got a nice theorem here, and what we're going to kind of latch onto is the second piece. If A is invertible, then A inverse is unique. So we shouldn't be too surprised about this. With what we know about inverses with regular old addition and multiplication, inverses are unique, right? If I have a number and I say, well, what number do I add to get to the identity? Well, that number, there's only one of those numbers, right? It's -3. Or if I say, what number can I multiply by 3 to get to 1? Well, there's only one such number, and that number is 1/3, right? So we shouldn't be too surprised that inverses are unique. We also ought not be surprised too terribly much that equations have unique solutions. So that usually happens. Well, at least with linear equations, we have unique solutions. Okay, so anyway, we're going to latch on to part 2 of this, and we're going to be able to solve systems of equations using inverses. And it's going to be just so very convenient because, it seems like we're doing a whole lot of work for not a very big payoff, but we're going to see the payoff right now. So what these all look like, all of these look like that same thing we started out talking about at the start. They all look like this, right? Well, if I take this matrix here, or excuse me, if I knew what that matrix was there, if I knew what the inverse of this was, maybe call this A, if I put A inverse on that side, and if I put A inverse on that side, I'm going to have my solution immediately, right? Because, well, that's just the identity. So we have xy is alone on this side, and we just need the inverse of that matrix, which conveniently we found earlier on up the page here. Maybe refer back to what we did earlier to see that this was the inverse. But conveniently now we have the solution. It's right there. All we have to do is just multiply the two matrices. So if I do row 1, if I do row 1 times column 1, I've got 12 times 26. Ooh, that's an ugly 12. 12 times 26 plus -7 times 39. And we've got row 2 times column 1. Okay. And I don't know, we can do the scratch work here, right? We can multiply and add. I'm just going to do that real quick. All right, the magic of video editing, we have the solution here. So what this is saying is that 39 -13 is the solution to that system right there. And we didn't really have to do any work. After we solved the single, find the inverse of the one thing. Well, let's look at the next one down the line. So just to solidify the fact that this is convenient. So we've got the same setup on the left, but on the right-hand side, we just have this, right? So that means that our solution, xy, has to be the product of the inverse that we found earlier and this constant matrix, this one right here, right? Okay, so multiplying those together, what do we get? We get 12 times 0 minus 7 times -1. We get -5 times 0 plus 3 times -1. Okay, and this one's a little bit easier to do, right? We just end up getting 7 and a -3. So that says that 7, -3 is our solution up here. And plug it in. Show yourself that it makes it true. It does, right? 3 times 7 is 21. Minus 7 times 3, well, that's 0, right? 5 times 7 is 35. Minus 36, well, that's -1. Hey, we found the solution. How cool. So great, we solved this one just immediately. We also solved that one just immediately. We can do the same thing with this one, right? And the only difference is we're just changing these numbers right here, 7 and 5 now, -7 and 5. And if I change these guys around, it's the same thing, right? Because my inverse is the same. I'm just going to have -7 and a 5, and a -7 and a 5. And we can we can solve this one too real quick. All right, 12 times 7, that's negative 84, minus 35, and we've got 35 plus 15. So then we have, whatever this is. What is this? Negative 119 and 50. And then we can, plug those in and see if it makes it true. And it will. So, you can go ahead and verify that. So, yeah, the short-term payoff of finding a matrix inverse is not very big. But now that we have the inverse of this guy, we can solve any equation that, or excuse me, any system that involves that for a variable part, right? And that's, well, awfully convenient. So yeah, that's it for this section, and it for chapter 8. Right, we're done talking about matrices. So yeah, that's it. Let me know if you have any questions about this, or if you want to talk about any of these topics further. Otherwise, thanks for watching the video, and have a great rest of your day.